Okay, I want to do a problem. Again, this is from a Baron Johnson book from years ago, 2013. Um, Basically, you could think of it as this. If we were to draw a artillery piece, so, and we fire a bullet downrange, it's going to land here someplace. Basic physics problem, okay? And the only thing that's different with this one is we want to know the recoil force that's going to be formed on the gun and in which direction is it going to go. Okay, it's relatively simple, but you can take it back into a nice little vector system. So let's get a drawing made here. Assume the gun is at the um, orientation, and actually the other thing is I don't really need a negative y-axis because we're not going below that. And let's see, what else do I want on this thing? We're going to have a z like so. Z, x, and y. Okay, and we can always think of this like this on a map. So let's do a little squiggly spot here, okay? And we'll make that go north. And we're going to have our z, x here. And we're going to fire off in which direction? We are going off into the northeast quadrant. So if that's north, this would be east. And we're going to fire from here to there. Okay, and land that shell there, so it's going to arc like that. Okay. We're not so worried about the arc. What we're worried is what happens at the barrel and what happens to the reaction force. Okay. All right. So in this problem, we are given gun aimed at point A, which is 35 east of north, knowing the barrel of the gun forms an angle of 40 degrees of the horizon, and the maximum recoil is 400 newtons. Determine the x, y, and z components of that force. The value of the angles x, y, and z defining the direction of the recoil force. Assume that x, y, and z are directed respectively east, up, and south. Okay, so in this we need to write north, east, and this one will be south. Okay, and then we'll have a west over here. Okay. Time for a color change, and I think a ruler really for this. And actually, I'm going to get rid of that and do a much nicer line. Don't know why I keep trying to fight with this, but I do. I really want to be able to draw on this new surface with a nice pen and smooth lines. So we are going in this direction. Okay. And this is 35 degrees off the x negative z plane. Okay. And then we are, oops, sorry, I got that wrong. We are 35 degrees to here, to here. Okay, and then we are 45 degrees, and it's got to go. I can't deal with that vector. we're going to deal with that, yes. And it's this angle here that's 45 degrees. Okay, cool. It's not easy, and I'm actually looking at an example with that in it, but for you to figure that out, you need to pay really close attention to where you are in space here. Okay, but that is the gun. So let's do this. Gun barrel. Okay, and it will fire off into that direction over there. All right, cool. All right, so a couple things that can do to help us with this. Okay, so we know the force of recoil, and I'm just going to call that F because that's our original F, is 400 newtons. Okay, if we can actually take that and put it from three-dimensional into two dimensions, it will help us solve a lot of things quickly. Okay, so literally, wouldn't it be really nice if we could just operate in the XZ plane to solve this? Okay, so let's do this. We're going to call this one F of H, okay? And that's going to be our horizontal. So if we take the F and we bring it down into the horizontal, did I say 45? It is 35 and 40. Aha. Let's change that to 40 degrees. 40 degrees, okay? Then we are going to get 400 newtons cosine of 40 degrees, and that will give us an answer of 306.42 newtons. Now, let's put that in perspective here. So there's the gun barrel. Okay, here's our horizontal, and we just took the 40 here and depressed it on the XYZ plane. Okay. Draw some wheels on it, carriage, put a gun in it. So we brought it down into here. So literally we're now working in this here down into there, okay? And we know this is 35 degrees that way. And this is our negative z, and that's our x, okay? That's all we did. We just simply tried to flatten it out from all three dimensions at once into just two dimensions to make our life ever. Sorry, my headset cut out there. Make our life ever so much simpler in the process of doing this. Okay, so keep that in mind. You can, I don't want to say cheat the system, but you can game the coordinate system to make your life really simple. Okay, all right, so the component of f of x is equal to negative f of h. Okay, whoops, that's an h, not an x. And I want to use the sine of 35 degrees. Okay, because we're looking at the adjacent angle here, or the opposite side of this thing. Okay, and we're going to be plugging in 306.42 newtons negative. Okay, and we are then going to multiply times the sine of 35 degrees, and we're going to get negative 175. I'm going to make it 8 newtons. It's like 7.75 and keeps running down through there. Okay. Hey, another little thing, remember over on your comp paper, you can do f of x and then put in negative 175.8 newtons and underline it, and then you can actually find it faster in the long run. F of y is going to be negative f, because that is in the y plane all by itself, and that is simply the sine of 40 degrees. So negative 400 newtons sine of 40 degrees, and we get negative 257.12 newtons. F of y, negative 257.12 newtons. Underline it, and away you go. Now, z is actually going back into the horizontal vector that we created. Whoops. Boy, I want to put that in there, don't I? The f of h, okay, and that's going to be times cosine 35 degrees. So one of the things, as I'm filling in numbers here, it's really important that you keep track of where you are in space in terms of which angle you're using. Okay. So if you're doing anything that involves the horizontal force that we resolved out of the x and the z, you want to play with that. But if you're dealing with just the y, then you are straightforward to go with the original force. Okay, anyways. So when you get done with this math, you should wind up with 251.0 newtons. And 251 newtons is f of z. Okay? And underline that. So cool. Now we know the three magnitudes of the vector. Let's go find our angles. So how are we going to do that? Well, again, we're going to use the angles. Cosine of theta x is equal to its opposite over the hypotenuse. So f of x over f, and I'm going to cheat, just put numbers in here, negative 175 point, now what did I call it, 178, didn't I? 175.8 over 400, and we should get an answer there that will be equal to, well, just do the math out so you can see it. Theta x is equal to the arc cosine of negative 175.8 newtons divided by 400 newtons. And when we get done, we get an angle of 116.1 degrees. And that's theta x. Okay? Cosine theta y is going to be equal to f of y over f, and same trig, just different numbers. And this is 257.12, I used 0.12 newtons over 400 newtons, and we're going to get a value that is 130 degrees. Okay. Cosine theta z equals f of z over f, which is equal to f of z in this case was 251 over 400, and we're going to get a value, you can go out of there, get a value of 51.1 degrees. Okay, and those are our answers, and that is the solution to that. Now let's recap for a minute here, because what I do that was really odd and weird was this bit right here. All that is what makes this easier to do than any other way to do it. Okay, so I took the force, which is the F, that is cruising right here, and I turned it into a horizontal force by the 400 newtons times the cosine of 40 and brought it down to the x, z, in particular the x negative z coordinate. Okay, that allowed me to take and then break the x component out of the f of h. Okay, and then f of z is the other component of that, while f of y is still the original 40 or sine of 40 degrees to get that one. Okay. I think a couple times you try this, you'll find this useful, but I am sure if you have questions, please ask, and I will try to create something that will make your life easier. All right, have fun. See you in the next video.